Stumfels will give his third lecture on tropicalization of classical moduli spaces.
Okay, well, thanks for coming to the third and last lecture. So the first two lectures involved some optimization and statistics last time. So a question you can ask, what kind of math is this anyway? What kind of math am I doing? So here's mathematics, and maybe here are some adjectives that one could put before mathematics. Maybe applied, or or pure, interdisciplinary, computational, experimental. And I think these are linearly independent adjectives. So mathematics does not take place on a one-dimensional scale between pure and applied, but it takes place in a multidimensional space. So for example, the last talk on maximum likelihood was certainly very experimental, probably interdisciplinary, and perhaps a little bit applied, mixed between pure and applied. So the talk today will be quite different. So today, the talk will absolutely be pure. It will be a pure math talk, but it will be computational. So it will be a computational talk in pure math, and so there will be no statistics, no optimization, only pure mathematics. Let me start. My point of view is that algebraic geometry is the study of solution sets to polynomial equations. So I'm interested in zero sets or solution sets to polynomial equations. And let me start by solving a very simple equation for you. I'm just going to solve for you one equation in two variables. Let's try to solve the equation x plus y plus 1 equals 0. And let's do this over a field with evaluation. Maybe rational functions in one variable t, maybe the algebraic closure. So how could we solve one equation in one variable, but keeping in mind that this field has evaluation? Well, here's what we do. We look at the minimum of the valuation, so the order of vanishing of x, which I call big X, the valuation of y, which I call big Y, and 0, which is the valuation of 1. So the valuation of a rational function is simply the order of pole of vanishing at the origin. And this minimum, in order for this equation to hold, has to be attained twice. Okay, so this is called tropical geometry. And so this condition in the xy plane defines what is known as a tropical line. So this defines in the xy plane a picture like this. So for example, a legal point would be -2, -2, that's capital X, capital Y, and this represents points such as -1 over t squared, comma 1 over t squared plus 1, -1. So I have found a solution to my linear equation, and I'm organizing them according to their valuation. So this is called a tropical line. Okay, so if I'm interested in solving a system of polynomial equations over a field that has a deformation parameter t, or epsilon if you teach calculus, or p if you study number theory, or q if you like physics. So if you have a deformation parameter, that's how you would solve equations. So here's the plan for today's lecture. So I like to explain the title, Tropicalization of Classical Moduli Spaces. I'm going to do that in 3 stages. First I'm going to explain tropicalization. Then I'm going to explain moduli spaces. And then I'm going to explain classical. Everything I say today is in a paper with this title with these two co-authors, Jinchang Ren and Stephen Sam. Okay? Are there any questions about tropical geometry? So tropical methods are by now widely known. This is a tropical line. So I'm simply solving this. A solution set to such an equation is called a line in the plane. I'm just drawing the line in the plane. Okay? Okay, that's clear. So let me define tropicalization. So in general, we don't have just one equation in two variables that's linear. In general, we have many equations in many variables that are non-linear. Say we have variables x1, x2 up to xn, and we organize our given equations into an ideal in a polynomial ring. Now, if I assign weights w1 to the variable x1, w2 to the variable x2, and so on, then every polynomial has an initial form, a lowest form with respect to those weights. And the ideal generated by all lowest forms is called the initial ideal. So for example here, if I have just my one equation, and if this is my equation f, it's my one polynomial f, then the initial form with respect to -1 is x plus y. X plus y, so this is a point, or maybe let's do it -2, -2. So this is a legal point, it lies here. So the tropical variety of my ideal, of my system of equation, is the set of all weight vectors w in R to the n, such that the initial ideal contains no monomial. Okay? That's the definition of the tropical variety. So this one, x plus y, is not a monomial, so therefore this half ray is in the tropical variety. Now, it is always the case that this tropical variety is a balanced polyhedral complex. There's a little bit of a twist. So K in general is a field with evaluation. So when you define your initial ideal and your initial forms, you have weights for the variables. So xi has variable wi. But when you look at the valuation of a monomial, you have to add in the valuation of the coefficient. But the most important sentence here is that you can compute this using software, GFan. So GFan for Grobner fan is a piece of software that you can download, and you type in any system of polynomial equations, any ideal in n variables, you hit a button, and out comes a polyhedral complex. Now, if the given equations have zero valuation for their coefficients, then the tropical variety is a fan. Right here, there was no t in the coefficients, so this is a fan. A fan is a finite union of polyhedral cones that fit together nicely. And in any case, the tropical variety always has the same dimension as the classical variety, and that's part of what's now known as the fundamental theorem of tropical geometry. So the fundamental theorem of tropical geometry says that the tropical variety reflects the classical solutions and that these objects have the same dimension. So the tropical variety is a polyhedral space of the correct dimension. So for example here in homogeneous coordinates, maybe if I have a homogeneous cubic polynomial like this, I look at the principal ideal generated by this equation, and I type it into GFan, and I ask GFan, plot the tropical variety. Out comes a fan, a one-dimensional fan with these 6 rays. These are the possibilities for the minimum of being attained twice. So the tropical variety is the set of all points where the minimum is attained twice over all infinitely many polynomials that vanish on the variety. Okay, so that's tropicalization. So any classical variety can be tropicalized, and you can compute that. This is a computational talk after all, by typing your equations into GFan. Please interrupt me with questions. So today we're going to go a little bit deeper than the last 2 lectures. Yes?
Can I ask for the definition of initial ideals again?
Yes, the definition of initial ideal. So if I have a polynomial, f, it has a bunch of terms. So each term looks like this. Ca, x1, ai1 up to xn, an, plus, plus, plus. So then this one has a weight. So the weight of this monomial is A1 W1 plus AN WN plus the valuation of the coefficient. Possibly, that's the weight. The initial term, so the initial of F is the sum of all terms of smallest W weight. Okay? I'm cheating a little bit here, you know, in the mixed characteristic case this isn't quite correct, but just for simplicity. And then the initial ideal is the ideal generated by all initial forms where F runs over all infinitely many polynomials in the ideal. Okay? So that's the initial ideal. The initial ideal is generated by the initial forms, so it's the usual definition that you know from Grobner bases, but here we just have weight vectors rather than monomial orderings. Okay, that answer your question? Okay, that's tropicalization. So often when I talk about tropical geometry, people ask me, can such and such be tropicalized? Of course it can. As soon as you can express it in polynomials, it can be tropicalized. Right? Whether the combinatorics is nice, interesting, and meaningful, that's another question. But if you have something that can be expressed in polynomials, it can be tropicalized. Right? How do you do it? You type it into GFAN, you hit the button. Okay? So today we're going to talk about pure computational pure math. Okay, moduli spaces. So let me give you an example of a very simple moduli space. So you might have heard, I hope there are number theorists in the audience. So number theorists study things like modular curves. So whatever a modular curve is, presumably it's a moduli space. So let me give you an example of a modular curve. So x5 is an example of a modular curve. It's the projective line with 12 points removed. Okay? So this binary form defines 12 points in P1. By any case, this is essentially P1, and I'm going to call that the modular curve x5. Now, luckily, some of you were in Christian Ranestad's talk, and 90 minutes ago, Christian talked about the elliptic normal curve in P4. He explained the elliptic normal curve in P4, and for every point in this punctured line, there will be an elliptic normal curve, and it's given by this equation. Okay? So I pick a point in here on that line with homogeneous coordinates a, b. So a and b are fixed scalars. So then I form this skew-symmetric 5 by 5 matrix. I form this skew-symmetric 5 by 5 matrix, and my equations say the rank of this skew-symmetric matrix is at most 2. Now you know from linear algebra that a skew-symmetric matrix of odd size has determinant 0, right? So a matrix like this can either have rank 0, 2, or 4. So generically it has rank 4, but I want the 4 by 4 subfaffians, the 5 4 by 4 subfaffians to vanish, and this gives me a system of 5 quadratic equations on P4. And the solution set is a curve, and that's an elliptic curve. That's an elliptic normal curve. Okay? No, elliptic curve of degree 5. Now I want to look at the universal family. I also want to vary the point in the AB baseline. I get a surface. Right? So if I have a family of one-dimensional family of curves, that's a surface. And it's the surface in P1, that P1, times the P4 with coordinates x0, x1 up to x4, given by this condition. Now let's tropicalize this. Let's calculate the tropicalization of the universal family. So what do? We take these equations. There are 5 equations in the x's, a's, and b's. We type them into GFAN. We say calculate the tropical variety, and out comes a picture like this. Okay? Now, what is this picture? This is the Petersen graph. And the Petersen graph, so here the coordinates are labeled by the entries. So this Skewsymmetric matrix has entries 1, 2, 1, 3, and so on, right? So there are 10 off-diagonal entries corresponding to this. And in fact, the surface, the tropical surface, is the cone over the Petersen graph. So earlier we talked about the tropical line. So I'm going to save one dimension. So this is, I think about this as the cone over 3 points. Okay, so this picture, the line, this one-dimensional fan, is the cone over these 3 points. 3 points for a topologist like Professor Koh, that's a wedge of 2 zero-dimensional spheres. It's a bouquet of 2 zero-dimensional spheres, and I cone it, I get my tropical line. That's a bouquet of 6 one-dimensional spheres. I cone it, and I get a surface. I get the tropic, and it's that surface. Okay, that's the surface. But now let's look at the modular properties. Let's take that surface and project it onto the AB line, and then the picture looks like this. So for a fixed point on the tropical AB line, so if I fix the valuation of A and B, the fiber will be a curve. Right? If I have a two-dimensional fan and I map it onto the line, right, then every fiber will be a graph, and the graph will be the tropicalization of that elliptic normal curve. So this is the picture. Now on this side, if the valuation of A exceeds the valuation of B, I'm picking the pentagram out of this. Down here, on the other side, I'm picking the pentagon, right? So this Petersen graph outside has a pentagon, inside has a pentagram. Okay? Now I'm just showing this little picture. Really, the Petersen graph has more symmetry. The Petersen graph has 12 five-dimensional cycles. And to do this really correctly, I would have to take P1 minus the 12 points. So I have to have 12 fins down here. So each of these 12 points selects one of the 12 5 cycles. But here in this cartoon, I just have the pentagram on the right and the pentagram on the left. So this is the universal family over the universal family over this modular curve. Each fiber is an elliptic normal curve. So this is a version of the J line for number theorists. And each fiber is the tropicalization of the elliptic normal curve that the Christian Ranestad explained 95 minutes ago. Now this is a very famous example in mathematics. So one of the famous books in mathematics is Felix Klein's Lectures on the Icosahedron from 1888. Where is the icosahedron? This is the icosahedron. Right? The 12 roots of this equation on the unit sphere form the vertices of an icosahedron. So this, if you think about P1 over the complex numbers as the Riemann sphere, then the 12 roots that I'm taking out, they are the vertices of an icosahedron. And so the icosahedron is a highly symmetric object. And let me think about this as an arrangement of 12 zero-dimensional hyperplanes in a one-dimensional space. Okay? So this is an example. Okay? This is an example of a moduli space and of the universal family of that over that moduli space drawn in G-fan output. Any questions? We can go very slowly today. I only have 15 slides, sir. Pardon me?
Does lectures on the icosahedron discuss moduli?
Well, they weren't called that in the 19th century. Yeah, certainly from the 19th century point of view, from Felix Klein's point of view, this would be an example of a moduli space. So a little later we're going to talk about other kinds of moduli spaces. I think the terminology wasn't there, but certainly this is an example. And if there are official number theorists in the audience, so this parameterizes not elliptic curves, but elliptic curves with a level 5 structure. So there's a little bit of decoration. Okay? Yes?
Called for the modular space back then? Were there a term that refers to the modular space?
Well, people did use the term modular, so people use the term modular, but not in a technical sense. So people would call this a modular curve, or they would talk a modular surface, but I think there was not a precise notion of, coarse moduli space or fine moduli space. And I'm gonna, so this is my definition. So my definition of moduli space is by way of one example. So I gave you tropicalization by way of 2 examples, or 2.5 examples. I gave you moduli spaces by way of 1 example. So for me, this X5 is an example of a moduli space. Okay? So I've now defined everything in the title of this lecture except for the adjective classical. So now on the next slide, I like to define the word classical. Now, classical in this lecture has at least 2 different meanings. The first meaning of classical is classical as opposed to tropical, right? So tropical means I do the min plus algebra. So in tropical math, 3 plus 5 is 3, and 3 times 5 is 8. That's not classical, that's tropical, right? In classical math, 3 times 5 is 15, and so that would be classical as opposed to tropical. Refers to moduli spaces over a field, or maybe over a ring, Noetherian ring, the usual setting of algebraic geometry. The classical setting is moduli spaces over a field, and classical as opposed to tropical. The second meaning of classical, I will mean today, all the moduli spaces that I will present today were essentially known in the 19th century. So some people, define classical as what happened before my PhD. I will define classical something that happened in the 19th century. Okay? So by classical, I mean 19th century. Now, as the drama unfolds, let me first give you the cast of characters in this drama. Okay? So here are some names of moduli spaces. So these are names of moduli spaces. So M for moduli. So this is the moduli space of genus 0 curves, Riemann surfaces with 6 marked points. M2 is the moduli space of genus 2 curves. Okay? Again, we saw some genus 2 curves in your lecture. And these parentheses 2 and 3, this refers to level structure. Now, I'm not going to define level structure. Maybe this will happen tomorrow. Tomorrow there's a lecture in this department on moduli of hyperelliptic curves. I saw, and I don't know what the speakers in the audience. I will not define level structure except to say whatever this is, it makes it nicer, right? So as I go down here, I put these parentheses, it makes it nicer. And nicer for me means algebraic geometry is the study of 0 sets of polynomials. So I don't like to worry about stacks. Okay? So I don't want to worry about quotient singularities and stackiness, and therefore putting this extra decoration on makes it nicer. Now these A's is basically the same thing. These are moduli of principally polarized abelian varieties, and in genus 2, essentially every abelian surface is a Jacobian, unless it's a product of 2 elliptic curves. So I will pretty much identify these. So the cast of characters are Jacobians of curves, abelian surfaces, maybe Del Pezzo surfaces. We did something really difficult 98 minutes ago. We blew up 8 points in the plane. I might blow up 6 points in the plane. I'm going to do something easier. Okay? Now, these things in the 19th century, they had names. So there's a Segre cubic, Igusa quartic, Burckhardt quartic. Burckhardt was a student of Felix Klein, and so on. And so I will talk about these varieties. Now the final cast of characters are groups, reflection groups. So in this game, to correctly draw the tropical pictures, it is essential that you work with an embedding in a highly symmetric embedding in a projective space, and you have to have some intrinsic symmetries. So the spaces that you have, they have some intrinsic symmetry. So for example, if you look at this, it doesn't look like much, right? But this thing intrinsically has the symmetry group of the icosahedron. I'm sorry, of the icosahedron, right? So this looks like a harmless binary form, but what you're supposed to see is the symmetry of the icosahedron. Okay, so therefore, when we talk about modular varieties, there will be a lot of symmetries, and these are the names of Weyl groups. So A5, E6, and E7, we're going to be interested in the Weyl groups of those root systems. Now, those you've probably seen. This one you may have not seen. So G16 and G32, these are complex reflection groups. So over the real numbers, the notion of reflection, well, along a hyperplane, it's an involution, right, with all but one eigenvalue is, and then it's only one eigenvalue is -1. Over the complex number, you can rotate around the hyperplane by roots of unity, and they were classified in the 1950s by Shepard and Todd, and today we're going to particularly see this reflection group G32, and G16 is the incarnation, it's the icosahedral group in its complex reflection representation according to Felix Klein. So in its guise on the previous slide, that would be G16. Now, our moduli spaces, all the moduli spaces in today's talk, are parametrized by monomials in linear forms. That's very important. So every variety is going to sit inside Pn, and it's going to be parametrized from d-dimensional space by monomials in linear forms. So we first, all our examples, there will first be a linear map followed by a monomial map. And then we're going to be interested in the closure. Having that makes tropicalization very, very easy. Makes it a purely combinatorial process. There will be a lot of combinatorics in this talk. So if we have a variety that's given in this form, first a linear map, then a toric, then a monomial map, then we can tropicalize very easy. Now let's agree that the Felix Klein example is of this form, right? So what's on the icosahedron? What's D, M, and N? Well, D is 1. Right? So my modular variety starts out in P1, but then I have a linear map into P11. What's the linear map? Well, those are the 12 points. It's just the valuation at the 12 points. I have an arrangement of 12 hyperplanes in P1. Well, if I have an arrangement of hyperplanes, 12 hyperplanes in P1, that's a linear map from here to here. Now, there's a natural way of grouping them in pairs. So there's a map, you know, into P5. There's a natural monomial map. And really, you know, the modular variety is the image over here, okay, in this symmetric. And then here on this space, the icosahedral group acts by permuting coordinates. And then we see the beautiful structure of the Peterson graph and the cycles on the Peterson graph unfolding in that bigger space. Any questions? Okay, so now I've defined the title. So we're 30 minutes into the talk. Talk is about tropicalization of classical moduli spaces. I've defined tropicalization, I've defined classical, and I told you what our moduli spaces are. So let's go a little bit higher. Let's move on from dimension 1, maybe to dimension 3. So let's start with the root system. So root system A5, this gives us the reflection representation of the symmetric group S6 on 15 hyperplanes. So let me look at the equations. Xi minus xj for all 15 pairs I and j. Okay? Now it looks like, so these are hyperplanes to the origin in R6 or C6. So this looks like a 5-dimensional projective space, but really, you know, these linear forms, they span a 5-dimensional space of linear forms. So this is really a P4. Right? So these are functions, these are linear forms defining 15 hyperplanes in P4. Okay, so whenever today, in the next 45 minutes, whenever I give you a hyperplane arrangement, if I give you a hyperplane arrangement, 15 hyperplanes in 4-dimensional space, you should think about the linear map. There's a linear map, you know, from P4 to P14. So the linear map takes the x coordinates and here maps them to x1 minus x2, x1 minus x3, x1 minus x4, blah, 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 x5 minus x6. That's my linear map. Okay? Now certainly on the image I have the symmetric group acting. Right? So certainly I can permute the coordinates. Now this image, by the way, what's the ideal of the image? Well, the ideal of the image is Zij, so I call the coordinates Zij here. Well, the ideal of the image is given by linear trinomials, Zij minus Zik plus Zkj. That's the ideal. Okay? That ideal, this degenerates from a tropical basis. So let's tropicalize the equation. So let's pretend you have your iPhone and you have GFan running on your iPhone, and you type in these equations, Z12 minus Z13, and then you say tropicalize. Okay? And what do you get? Well, you get the space of ultrametrics. Now, why is that? Well, let's do it again. Okay. So let's look at an equation. Z12. So we want to solve a linear equation like this. Okay. Now, let me use, just for a moment, for the sake of illustration, let me use not min plus algebra, but max plus algebra. So let me say the maximum of the valuations, the maximum of D12, D13, and D23 is attained twice. Right? That's how we solve this over a valued field. What's that? Well, that's the space of ultrametrics, or this is the space of rooted phylogenetic trees. Okay, so suppose you have a rooted tree, and I will not speak about biology because this is a pure math talk, but in p-adic analysis, when you study fields with valuations, you see trees like this all the time, and so you might have 3 p-adic numbers, and then the pairwise distance satisfies this, right? So the distance from 1 to 2 equals the distance from 1 to 3 and exceeds the distance from 2 to 3. So this is some fixed length. This is a rooted phylogenetic tree, and it's the space of trees. So we see that the tropical variety is the space of ultrametrics on 6 elements, or the space of rooted phylogenetic trees on 6 taxa. Now, if you take enough combinatorics classes, such as the one that Professor Holmson is offering, it's very easy to realize this as a fan over a simplicial complex with F vector 56, 490, 1260, and 945. So this is a 4-dimensional fan over a 3-dimensional simplicial complex with 945 tetrahedra. Okay, one for each metric tree, each rooted phylogenetic tree on 6 taxa. So if you have 6 taxa, then 945 possibilities. So this will be the output of GFan. So again, at the very beginning of this talk, we talked about the tropical line, which was the cone over a 0-dimensional complex. Then I drew the fan over the Petersen graph, 1-dimensional complex, and now we have this 3-dimensional complex. So now we're not there yet. All we've done so far, we mapped this in, right? So now the linear map always gets followed by a monomial map. So to make a classical moduli space, we follow the linear map by a monomial map. So I have to tell you what the monomial map is. And there are 2 possibilities. The first monomial map is like this. I take 15 cubic monomials in my 15 z variables, and the monomials correspond to the tripartitions. Okay? 6 people go to a party, and you want to form 3 pairs. There are 15 ways of doing that, right? 6 people at a party, so you can go z12 times z34 times z56. There are 15 possibilities. That's the monomial map. Okay? The image of this is called the Segre cubic. Now, evidently, the image, so this image turns out to be a 3-dimensional variety, but my Weil group, my symmetric group, acts on the image, right? My 15 ways of going to the party, the symmetric group acts on this. And again, in this talk, we're always always look at varieties as zeros of polynomials. So I should tell you what those polynomials are. The prime ideal is generated by 10 linear trinomials and 1 binomial cubic. But the point here is that I've retained the full symmetry. There's another thing you could do. You could say the 6 people who go to the party, you don't want to break them into 3 pairs, but into 2 triples. Right? You want to form 1 triple and another triple. There are 10 ways of doing that. And that gets represented by 10 sextic monomials. So here you have 1, 2, 3 together, 4, 5, 6 together. You know, here 1, 4, 6 goes together, and 2, 3, 5 goes together. Right? So that's the Igusa map that goes into P9. Now at the bottom, there's a little proposition. First of all, these images are 3-dimensional varieties. They're 3-dimensional spaces. And on the open part, they are the same. So by S0, I mean the image, but I'm only interested in those points where all of these coordinates are non-zero. So S0 is the very affine variety that I get by requiring that the coordinates are non-zero, and then these multiplicative maps have the same kernel, and therefore S0 is isomorphic to I0. They are the same threefold. Now that same threefold has at least 2 modular interpretations. Either you could interpret this as M06, the moduli space of 6 labeled points on the line. That's a 3-dimensional space. Right? If you have 6 points on the line, projectively the first 3 points are determined. You have 3 more degrees of freedom. So the space of 6 points on the line is a 3-dimensional space, and it is that space. I have given you a parametrization and equations. But it can also be interpreted as the moduli space of genus 2 curves with level 2 structure. Level 2 structure means the following. So the way you can make a genus 2 curve is you can double cover the line at those 6 points. So if you have a double cover of P1 branched at 6 points, that's also a genus 2 curve. And if you label those points, then that's a level 2 structure. So this is the space. So I've given you a highly symmetric embedding either into P9 or P14, your choice, of these moduli spaces. Well, now we can tropicalize them, right? So for example, the Segre, we have a linear map from P4 to P14 followed by this monomial map. Now one reason you will want to tropicalize is because the tropicalization automatically gives you a compactification. Okay? Now these varieties, mind you, they're open varieties. They're not compact yet. Okay? Now people in algebraic geometry and topology for that matter often prefer to compactify these varieties, and they put effort into finding good compactifications. Here it's effortless. You just type them into GFAN and GFAN returns the compactification. So how does this go in general? So if X is a subvariety in Pn and X0, the open part where the n+1 homogeneous coordinates are non-zero, well, trop X, the output of GFAN, the tropical fan, is a fan. Okay? So it defines a toric variety, compactification of torus. Just take the closure in that toric variety. That turns out to be compact, and that's called the tropical compactification. So for example, in the very special case when the given variety is a hypersurface, then the tropical compactification is what's sometimes called the compactification from the Newton polytope. But tropical geometry really is the theory and practice that makes Newton polytopes obsolete. Okay, that's why we're doing tropical geometry. Okay, great. So we have a compactification. What is it? Well, unsurprisingly, it's one that's well known. So the tropical compactification is the same as the Deligne-Mumford space M06 bar, and it can be obtained either from the Segre cubic or from the Igusa quartic by an appropriate blow-up. So S and I are singular in the boundary, and there's a well-known situation where we blow this up. Combinatorially, this is quite beautiful because the map so here we have this fourfold, here we have the tropical linear space of dimension 4, and this tropical linear space maps here onto this threefold, and this tropical map is simply erasing the root. So making this rooted tree unrooted. So the tropical Segre cubic is the image of the space of ultrametrics under the 15 by 15 matrix. A monomial map tropicalizes to a linear map, right? So tropicalization is taking the logarithm, so a monomial map becomes a linear map. So I simply take this tropic linear space and I map it in, and we get a simplicial complex with 105 triangles, and that's our tropical, compactification. So that's also our first non-trivial example. Now, even in this example that seems to be so very well known, there's something nice that we can observe, and let me explain that by this diagram. So our tropical moduli space, M2 or M06, well, we agreed there are 105 maximal cones, right? 105 triangles. There are 90 triangles that look like this, that correspond, there are 15 triangles that look like this. This is called a snowflake tree. And there are 90 triangles that look like this, that corresponds to a caterpillar tree. And then there are lower dimensional strata. So these are the trivalent trees, and then there are lower dimensional strata. These correspond to edges, and so on, right? So we have the simplicial complex, the space of trees with the 105 triangles, so on, 105 edges, and 25 vertices. Now in moduli space, the tropical moduli are the edges, the lengths of the interior edges, right? So this is a three-dimensional space. So this is the tropicalization of 6 points on the line. Okay? Is this clear? So if you give me 6 points on the line over my field with the valuation k, then you have that picture. Every choice of 6 points on the line, over the rational functions or the p-adics, gives me a metric tree with fixed edge lengths. And these edge lengths are the parameters in moduli space. But now I have a map, right? So I have a map that forgets the labeling. I have a map from M02 with the 6 points labeled to M2 where the 6 points are not labeled. Now I can tropicalize this map, and I can tropicalize it on the equations I've given you, and I just read off what I get. And so trop M2 is the space of metric graphs of genus 2. Okay, so this is a metric graph, right? This is just a graph with edge lengths. And the map goes like this, right? So I take these edges and I wrap them around, and I use those edge lengths. So there's a map that takes a metric tree with 6 sleeves to a metric graph of genus 2. Likewise here's a little bit of structure. So this interior edge gets doubled in length, and then this edge gets doubled, and these lengths are halved. And then the same happens on lower dimensional strata. This point, gives a little genus 1 point. So there's a combinatorial theory of a synthetic combinatorial theory of tropical moduli spaces developed by Mikalkin and many other people. And what we're doing is we're having an equational description here, and we're mapping it in. Okay, so this is one thing that you already get for 6 points on the line. And the talk that is advertised in this department for tomorrow deals with hyperelliptic curves in general, right? So in general, you can do this in general. So in general, if you have a map from M0 to G plus 2 to the hyperelliptic locus in MG, and that's exactly the rule that gives this tropicalization. Okay, so this was my first example. the symmetric group S6 acting on the 15 hyperplanes.
Can we get all the diagrams from let's take the second diagram?
Yes, so then I get to this stratum. Then there are more pictures down there. So all the way at the bottom, all the way at the bottom, at the very bottom, the most special stratum on the left side looks like this, and this on the right side looks like this. The most special stratum in the space of metric graphs of genus 2 is a single node labeled 2. And then, so this is the most special. That corresponds to the empty simplex in this two-dimensional simplicial complex, right? So this is the space of metric graphs of genus 2, and these are the two general types. So this is tropical moduli space. Of course, in topology, people usually look at enhanced version of this. They look at the outer space. Outer space is the outer space to moduli space. So outer space to this tropical moduli space is like Teichmuller space to classical moduli space. Let me say this again. Teichmuller space maps to moduli space. Tropicalized Teichmuller space, which is outer space, maps to tropical moduli space. Okay. We remember sort of a homology basis for the cycle, free group action. Okay. That clear? So that was 15 hyperplanes in 4 space. Now let's move on. So we've talked about 6 points on the line. Let's see whether we can also understand 6 points in the plane. Let's talk about 6 points in the plane. Now, I'm going to, of course, if I have 6 points in the plane, I can write the homogeneous coordinates as the columns of a 3×6 matrix. I claim that I can always choose my 3×6 matrix like this. 1 di cubed. Okay? So I claim if you have 6 points in the plane, so the space of 6 points in the plane, let's agree, is a 4-dimensional space. It's a 4-dimensional variety, right? So the first 4 points is a projective basis, and then the 5th point and the 6th points. So you have 4 degrees of freedom in picking, 6 points in the plane. Okay? Now, up to a projective transformation, I claim you can always do this. Any 6 points in the plane can be written as these points. In fact, non-uniquely. Okay? This is you can always put your 6 points and a nodal cubic. I'm sorry, on a cuspidal cubic. Okay, now to talk about this invariantly, let's pass to invariant coordinates. Let's look at the maximal minors, the 3×3 subdeterminants of this matrix. And you notice that they factor beautifully into linear forms, right? Each 3×3 subdeterminant is a quartic polynomial, but it factors into linear forms, right? It's a Vandermonde determinant, and then there's a tiny little Schur function over here. Okay? That factors into linear forms. Now let me also record one more condition. There's one more geometric condition that you can have on 6 points on the line, on the plane. 6 points can either be on a conic or not. Okay? So the condition for them to lie on a conic is that this product of minors is equal to that product of minors. Well, if you substitute in, right, so this is a polynomial of degree 16, but it factors into 16 linear forms, namely those 15, the one we saw a couple minutes ago, times one more linear form, which is the sum of the d's. Okay, so if the points are distinct, then this is the condition, the vanishing of this sum of the di's is the condition for the 6 points to lie on a conic. Now let's look at all the linear forms we have. We have 15 linear forms like this, di minus dj. We have 20 linear forms like this, di plus dj plus dk, and we have one more. So altogether, we have 36 linear forms, homogeneous, and 6 unknowns. So we have an arrangement of 36 hyperplanes in P5. That is E6. Okay? If you didn't know E6 before coming to this talk. Now you do. This is E6. Okay? This is the reflection arrangement of type E6. It's those 36 hyperplanes. Okay, well, that's great, right? So we have 36 hyperplanes in P5. The name of this arrangement is E6. So like always in this talk, that's a linear map from P5 to P35, right? So I've defined to you a map from P5 to P35. And so all I need to do to get to the appropriate moduli space, I need to tell you monomial map. And I'll tell you, I'm going to give you 40 monomials in those 36 linear forms. I'm going to give it to you not on the next slide, but one more slide. Okay? So the variety I'm going to construct, we decided to call the Yoshida variety. So we had a lot of discussion how to name these things. So most of our moduli spaces are named after dead German mathematicians, like Klein, Burckhardt, Göpel. Now this guy is an alive Japanese mathematician. He's actually very close from here. He still lives in Kyushu for many, many years. And he studied hypergeometric functions. And this is implicit in Koval's work, but he was the first to describe this embedding. And he was interested in hypergeometric functions. So we called it the Yoshida variety. But before I tell you the monomial map, let me tell you about this linear space. Right? So I have a linear space, but now we need to tropicalize the linear space. So how do we do that? Right? How do you tropicalize a linear space? Well, tropicalizing a linear space is exactly the same thing as calculating its matroid. Here we have a matroid. Right? I've given you a matroid of rank 6 on 36 elements. I've given you 36 hyperplanes to the origin in 6 space. So now GFAN won't do that, but we have very lot of symmetry. And you know, some classes here teach how to find matroids, and so here's the answer. Right? There's the E6 matroid. So matroids have flats, and this is a list of the flats of the matroid. So the rank 1 flats, they correspond to the 36 hyperplanes. The rank 2 flats correspond to codimension 2 strata, intersections of 2 hyperplanes. So those are codimension 2 linear spaces, and so on, all the way down, you know. So these correspond to in points of intersection of these hyperplanes in P5. So they are grouped in orbits, right? I have this group acting. So for example, you know, this codimension 4 stratum, there are 1080 in the orbit. Now here's the deal. Flats in a reflection arrangement correspond to parabolic subroot systems. There's a beautiful theory that tells you how to list the flats. So these are subroot systems, right? So the root system, what's a root system? So the root system we're talking about here is a picture like this. We're talking about, so our discussion here is about this picture. That's called E6. And you know, maybe you have some D4. Or maybe you have some A4. Right? So these are called subroot systems. Okay? Now, among these subroot systems, the ones that are most interesting are the irreducible subroot systems. And here the numbers are in boldface. Here, by the way, I have the equations of representative flats. So for example, a representation of this codimension 2 flat is the intersection of that hyperplane and that hyperplane. Okay? So you calculate a table like this. Now, the tropical linear space, also known as the Bergman fan, well, it's a 5-dimensional fan in tropical projector 35, but it has 750 rays, and the rays are the irreducible subroot systems. It's always true, right? So if you add up, you know, you look at the irreducible subroot systems, this one plus that one plus that one plus that one, these are the rays of this fan. So this is a cone over a 4-dimensional simplicial complex, and this simplicial complex has 750 vertices and a whole bunch of tetrahedra. Okay, so that's how you do that. So of course, we have hyperplane arrangements with lots of symmetry. We must calculate the matroid. Tropicalizing the image of the linear space is essentially equivalent to calculating the matroid. Now, equipped with that, so now we've calculated tropically the image of the linear map. So now all I need to do to get the Yoshida variety is I have to tell you the monomial map. Okay, well, here's what you do. I have to tell you 40 monomials, and you take 30 bracket monomials like this. So this gives you equations of degree 24. And then you take the conic equation times, again, these are our 6 people at the party into 2 triples. There are 10 ways of doing that. Turns out, when expanded into the D's, they all are divisible by these 15. 24 minus 15 is 9. So we have 9 products of linear forms in the roots. So we have a map, a canonical map, monomial map from P35 to P39, given by 40 products of 9 tuples of roots. Well, turns out that this has a modular interpretation, so why not? The open image, the open part of the image, is known as the moduli space of marked smooth cubic surfaces. So cubic surface in 3 space you get by blowing up 6 points in the plane. I have parametrized for you 6 points in the plane, and so that's it. Now then the closure, the Yoshida variety, here's a nice description. You know, it's the intersection of a 9-dimensional linear space, a 15-dimensional toric variety, that toric variety. That's the intrinsic torus, and this resulting tropical compactification is the Naruki compactification of the moduli space. So this was described, for example, in an Inventiones paper by Hacking, Kiel, and Tevelev. And here's a little bit of fine print. So the tropical Yoshida variety is the image of the Bergman fan. So this is the structure on the previous slide under the linear map given by the 40 by 36 matrix, that 40 by 36 matrix. Okay, I have this Bergman fan, this 5-dimensional fan, I map it in, and I get a 3-dimensional cone. I get a cone over a 3-dimensional simplex, and this has 1,215 tetrahedra and 76 vertices, and these 76 vertices, they come, you know, in a nice way from these subroot systems. Okay, so this is what we do with 6 points in the plane. So what have we done? We talked about Felix Klein's icosahedron, we talked about 6 points on the line, and we talked about 6 points in the plane. I'd like to give you one more example. So the last 2 lectures I went under time. This time I'm going to go a little closer to the time limit. Okay? So this is how you parametrize 6 points in the plane. And you automatically get it over any field, and tropical. So the last example is, oh yeah, by the way, I should say one more thing about this. You can do exactly the same thing for 7 points in the plane. If you do this with 7 points in the plane, you get the Göpel variety. That's a 6-dimensional space. It lives in P134. Can be also interpreted as the moduli space of genus 3 curves with level 2 structure. And there's an apparel theorem, so it's always an intersection of a linear space given by trinomials and an appropriate toric variety that represents the dense torus, the intrinsic torus, in the very affine Göpel variety. But most importantly, this gives us a representation of the universal family of cubic surfaces. Okay. Well, what's the story? You have 6 points in the plane. Each choice of 6 points in the plane gives you a cubic surface. Now, blowing up the 7th point, that 7th point parametrizes the cubic surface. So you have the universal family. So the Göpel variety is actually the universal family of cubic surface. And exactly, you know, this is the description. This is our cartoon, right? The cartoon from 40 minutes ago applies here. So down here, the base is the 4-dimensional tropical Naruki variety. So this is a 4-dimensional variety. That's the cone over a 3-dimensional simplicial complex with 1,215 tetrahedra. That's the base. Up here, I have a 6-dimensional fan. Well, I have a 6-dimensional fan mapping onto a 4-dimensional fan. Each fiber is a 2-dimensional surface, and it's, you know, these are exactly the cubic surfaces. So this is sort of significant because for a long time in tropical geometry, we have struggled to understand what's going on with the cubic surface in 3 space. Christian had a student, you know, a couple years ago who tried to understand what's really going on with the cubic surface in 3 space, what happens, you know, to the 27 lines. This gives a conceptual framework for understanding that, because we really have built the moduli space. Okay, my last example. Let's reboot. I have only one more example, and then the talk is over. Okay, so the root systems, the arrangements, the hyperplane arrangements I've shown you so far were over the real numbers. So I've talked about A5, E6, and a little bit about E7. Okay. Now I'm going to give you a complex reflection arrangement, and I'm going to give you the arrangement G32. Okay. I'm just going to throw this at you. Okay. So I'm going to give you an arrangement of 40 hyperplanes in P3. 40 hyperplanes in P3 over the complex numbers, or over any algebraically closed field that has a cube root of unity of characteristic different from 2 and 3. Okay? Well, what are these 40 linear forms? These are the linear forms. Okay? So the linear forms are, so the coordinates here are C0, C1, C2, and C3. And it's these, right? So these things. So for example, C0 plus omega squared C1 minus omega C2, and omega is a cube root of unity. So I use a cube root of unity, and I write down these 40 hyperplanes in P3. Okay? That's a reflection, that's a complex reflection arrangement. Now what are the names? What are the names? Well, you know, there is some analytic hidden theory. The talk tomorrow is about the analytic construction of Jacobians. So under the hood, there's an analytic theory. And these names reflect the underlying analytic theory. Underlying this is a vector space on 81 elements. So let's think about the vector space of 81 vectors. That's a 4-dimensional linear space over F3. Okay? Now that 4-dimensional linear space with 81 elements has 40 lines to the origin. Right? So if you're over F3, you know, a line through the origin has exactly 2 non-zero vectors. Right? So there are 40 lines to the origin. So the projectivization of this vector space has 40 points. These are the points. These are the names. Okay? So for example, you know, 1, 0, 1, 2, right? That's a line. 1, 0, 1, 2 is a point here, but I identify this with 2, 0, 2, 1, right? Which is just twice it. Okay? So on this finite vector space, these are the names. Okay? Now this is an even-dimensional vector space. An even-dimensional vector space, over a finite field or not, is a symplectic vector space. So there's a symplectic inner product on this vector space, and it's simply this. You know, you have 2 vectors x and y. You multiply them as x1, y3 plus x2, y4 minus x3, y1 minus x4, y2. That's the dot product. That's a symplectic inner product on this finite vector space. Okay? Now if you have a 4-dimensional vector space with a symplectic inner product, well, every vector is perpendicular to itself. That's a symplectic space. And a middle-dimensional vector space is a Lagrangian if any 2 vectors are perpendicular to each other. Okay? This vector space has 130 2-dimensional linear subspaces, exactly 40 of which are Lagrangian, and 90 of which are non-Lagrangian. See, if you are a middle-dimensional vector subspace, you have an orthogonal complement, right, in the inner product. that orthogonal complement either is the same as you or is different from you. If it's the same as you, you're Lagrangian. If it's different from you, well, then it's another guy. So there's 45 pairs of non-Lagrangians and 40 Lagrangians. Those 40 Lagrangians are the 40 monomials that I'm using to map in. Right? So my monomial map is given by the Lagrangians. So each 4 tuple, these are the 4 rays on a 2-dimensional space. Right? If you have a 2-dimensional space over the 3-element field, it contains 4 lines. So each of the 40 Lagrangians contains 4 lines, and I take those to be my monomials. Okay? So this is not some random crazy set of monomials. This is a very highly structured. I mean, there's the symplectic geometry of this 81-element vector space tells me what to do. Okay, now what should we do next, right? Well, we should compute the matroid, right? So now we have a rank 4 matroid on 40 elements. We did it, and we get the image is the so-called Burckhardt quartic, and again, it's the intersection of a toric variety, namely the 24-dimensional toric variety given by that monomial map, and that's the intrinsic that characterizes the intrinsic torus with a P4. And so in this P4 we get a quartic hypersurface called the Burckhardt quartic. It has a tropicalization. Whenever we have the tropical fan, and we do here, right? We have the tropical fan. We calculate the matroid. Then we take the image under the 40 by 40 linear matrix that I just described, right? We just take the incidence matrix of directions and Lagrangians, and we map in the matroid, the Bergman fan, and we get the tropicalization, and we recover what's known as the Igusa desingularization of the Satake compactification of A2. So this is the moduli space of abelian surfaces with a little bit of decoration. Here's the combinatorics. So the tropical Burckhardt quartic is a fan over a 2-dimensional simplicial complex with 880 triangles, 600 edges, and 85 vertices. 85 is 40 plus 45. 40 Lagrangians, 45 pairs of non-Lagrangians. Okay? So the entire, this encodes all of these F vectors, all this combinatorics encodes the symplectic geometry on this vector space. The Bergman fan, the matroid, has 170, so there's a 2-to-1 cover, this many triangles on the matroid fan. And it's always good to double check. So I found this very, very nice. So you look at the Euler characteristic of this. So you take this minus that plus that minus 1. You get 1729. Okay? But 1729 is 1 times 7 times 13 times 19. And those are the exponents of this reflection group. So if you study, reflection groups, real or complex, there's always something called the exponents. Those are the degrees of the invariance, the ring of invariance. And this also, of course, can be expressed as the leading coefficient, I guess, of the characteristic polynomial of the matroid. And it was very gratifying to see, that the product of the exponents matches this combinatorics. This, by the way, there is a choice of coordinates on this P4 that can be written like this. So let me record. This is one way of writing the quartic. So this is how you would find it in textbooks, such as Dolgachev's textbook. But I don't want to do that. I want to have it in P39 because I want my group to act by permuting on coordinates. Okay, you're in luck, right? So there are only 2 slides, right? So there's 14, 16. So there's one more slide with content and one more slide with philosophy. So let me give you the last slide with content. Now suppose you don't know what an abelian surface is. And let's suppose you don't know what a Jacobian of a genus 2 curve is. I'm going to tell you. I want to tell you what's an abelian surface, and I'm going to tell you all abelian surfaces on the next slide. I'm going to put my abelian surfaces, they're all going to live in P8. So I'm going to fix a projective space of dimension 8, and I'm going to put all abelian surfaces into P8 in a particular way. Well, first of all, what are the coordinates, right? You know, I'm a computational person. This is a computational pure math talk. We're computing zeros of polynomials. So I have to give you the names of the coordinates. And the names of the coordinates are x00, x01, blah, blah, up to x22. Okay? So the names of my coordinates, my P8, that's named by the two-element vector space. Okay? YF3, that's the level structure. So this 3 is the level structure. So I'm naming my coordinates by the 9 vectors in this 9-element vector space. Okay? Now let's consider the following 5 cubics. So again, these cubics, I don't need to remember anything. This tells me what to do. So F is the sum of the cubes. I'm just adding all the points in this vector space. And then I'm defining G01, G12. Well, these are the lines. Right? So what's this? Let's draw this vector space since we have a little time. How does this vector space look like? And I can think about it this way, you know, the affine structure. So here are my 9 points. Right? I go like this, like this, like this, like that, like that, like that's the origin. Okay? Then I go like this. Hope I'm not going to mess up. Those are parallel lines, and then this line is parallel to this line, and this line is parallel to that line. Right? So those are the lines in this affine space. And these are just the parallelism class of lines, right? So these 3 guys form a line, and these are the other lines that are parallel to it. So there are 4 parallelism classes of lines, each having 3 lines. So those are the G's. Okay? So now I'm going to look at the hypersurface. I'm going to take a random linear combination of those. So I'm going to say R times F, S01, so these are coefficients, R, S, this S, that S, that S, and I'm going to get a cubic hypersurface in P8. I'm going to call that the Koebel cubic hypersurface. Except the R and the S, that's a point on the Burckhardt coordinate. So I want my R and S to satisfy this equation. So I'm going to pick a point on the Burckhardt coordinate. How do I make points on the Burckhardt coordinate? Well, if I wish, you know, I can start in P3, right? Everything is driven by P3. You give me any point in P3, I map it in, and I get numbers. Okay? R, S, 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 S. Okay? Here's a theorem. So the singular locus of this cubic over any point in the open Burckhardt quartic is an abelian surface in PS, in P8. Okay? So if you give me, I have the 3-dimensional moduli space of abelian surfaces. I have given it to you, parametrized by P3. So you give me a point in P3, I write this down, I take the derivatives, right? So there are 9 derivatives, I set them to 0, I get 9 quadratic equations, that gives me an abelian surface. Now I told you, in genus 2, essentially every abelian surface is a Jacobian of a curve. Where's the curve? Well, there's the curve. The theta divisor on S is the tricanonical curve of genus 2, and I get it by intersecting this surface with a P4. And the P4 is given by this system of 4 linear equations. Right? So here's my numbers, my moduli numbers, R, S, that's the second row. And then here, you know, I write this down. Again, you can see the structure. It's always the same structure, right? That's an affine. So I write this down. The 2 by 2 minors give me 4 linearly independent equations. So I've given to you the curve and its Jacobian, and everything sits in P8. And, you know, we can draw tropical pictures. And the base of those tropical pictures, you know, is this very nice fan that has 85 vertices, 880 triangles. The vertices are labeled by Lagrangian and non-Lagrangian pairs and so on. Okay, so if you didn't know what an abelian surface is, this is the abelian surface. Okay? Every abelian surface comes this way. The talk is up. Let me conclude. My interest in algebraic geometry and in fact in mathematics is I want to understand zero sets of polynomial equations. I believe that this is useful both within pure math and contexts outside pure math, such as optimization, statistics, systems biology. There will be a colloquium 15 days from now on mathematical opportunities in systems biology. Very many good applications of polynomials in systems biology. But within the context of pure math, I believe that this applies to moduli spaces. So very often when you study moduli spaces, they are presented in either by geometric invariant theory or some other construction in a way that looks like they're not amenable to computing with explicit polynomials. I try to give a hint that in principle this can be done. Once you ask tropical questions, you get a very good sense of building tropicalization of universal families of moduli spaces and understanding the individual objects. So here in the very beginning we had the family of all elliptic normal curves over Felix Klein's punctured Riemann sphere. Then later we said we can also study the family of all cubic surfaces over the four-dimensional tropical Göpel variety. Now to build these spaces, to understand the structure, of course we need a very good grasp of combinatorics. We need in particular matroid theory. And what is combinatorics? Combinatorics is the nanotechnology of mathematics. And so today we talked about tropical geometry, and I thank for your attention.